Hello, today we're going to be doing a video explaining some examples of taking the antiderivative. I don't have a video posted yet on exactly what is the antiderivative, but basically a simple example of it is exactly like I said. The antiderivative is just the opposite of taking the derivative. You're taking a back step of taking the derivative. Like say you had your derivative of x squared equals 2x. It's going to go backwards and going to be x squared. So let's take a few examples. Say we have 3e to the 3x minus 5. We're taking the antiderivative of that. Notice that we have these two symbols right here. Anytime you're taking the antiderivative of a function, you're always going to have these two symbols right here. You cannot have one without the other. Okay, so say we have this function 3e to the 3x minus 5. We're going to want to make our variable u equal to this right here. We're going to make this kind of simple on ourselves. Okay, so now u is going to equal 3x minus 5. I'm going to want to take the derivative of u. Now, in order to take the antiderivative, you kind of have to take the derivative first of something of the original function. It's kind of a messed up way of doing it, but it works. So we're taking the antiderivative, or we're taking the derivative of u in that function. So now that's du. That's a constant, so that just turns to 0. That's 3x is just 3. That's leaving you with 3 dx du. You're going to divide both sides by 3 to get your dx, because that is the whole purpose of taking the derivative, is figuring out what your dx is equal to. In which case, dx is going to equal du divided by 3, which can also be thought of as dx equals 1/3 du. Okay, so now we have our dx. We're going to come over here and plug it back into our original function. So now we have 3e to the 3x minus 5 times 1/3 du. We're going to cross out these 3's, and now we're left with e to the 3x minus 5 plus a constant. Anytime you take the antiderivative of a function, the antiderivative is always going to be plus a constant. You don't necessarily know what that constant is, but it is there. So always at the end of every antiderivative, you're going to have plus a constant. Here's another example for you. Tan arc x divided by x squared plus 1. We're going to set our u to equal tan arc x. Take the derivative of u, should be 1 plus x squared dx. And I apologize about that. We're not doing that. We're taking, I apologize, x squared plus 1 is actually what we're setting our u to equal. That makes more sense. Take the derivative, find out 1 plus x squared du is equal to dx, and then we plug that back in. Sorry for the crappy eraser, but plug the dx back into here, and we find tan arc x divided by x squared plus 1 times x squared plus 1. You can go ahead and cross those out, and now all you're left with is arc tan x plus a constant. Because remember again, every time you take the antiderivative, you're always going to plus a constant after you find out what the antiderivative is. One last example, the antiderivative of e to the x divided by e to the x minus 1. We're going to set our u to equal e to the x minus 1. Take the derivative of u, find it's minus 1, that's a constant, that's just 0, minus 0. E to the x is always e to the x when you take the derivative. So now you have your du equals e to the x times dx, and then you can divide both sides by e to the x to find out that dx is equal to du over dx, or e to the x. We can also think this as 1 over e to the x. So we're going to plug this into the original function. Okay, so then we have e to the x divided by e to the x minus 1 times 1 over e to the x. You simplify. Okay, now you're just left with 1 divided by e to the x minus 1 du. You can take the log and just have log 1 minus e to the x plus a constant. Here's some examples of anti-deriving. Later on I'll have more videos explaining more on the antiderivative, what is it really, more examples of how to use it, and I will see you later.